So there's a few things that I want to go over in this video. First, I just drew some random function. And I want to highlight the different type of discontinuities that we can come across. For instance, you see how right here, it seems like we can draw like a vertical line, right? That is what we call an infinite discontinuity, because here is this vertical asymptote. But on either side, you see how sort of one goes down and one goes up? This is what we call an infinite discontinuity. I see another one over here. You see how the line goes, there's like a vertical asymptote? So in this case, they actually happen to go together. This is still an example of an infinite discontinuity. Infinite because it goes up and down forever. So this is an infinite discontinuity, and so is this. Now, you see how this roller coaster goes, and then it opens, and then it jumps? This is what we call a jump discontinuity. Also here as well. This is called a jump discontinuity. Now, here, it seems like there's no massive jump, but there's a hole here. There's a hole. And that's what we call a removable discontinuity. And you know what, to be honest, usually for a graph, when there's a hole, if you look either above it or below it, there tends to usually be like a solid dot. What that means, we'll discuss maybe in a different video or for a different time. But for now, infinite discontinuity, jump discontinuity, removable discontinuity, which is sometimes referred to as a hole. On that note, let me do one problem here that addresses the idea of a removable discontinuity. I want to look at this function here. Now the goal is to graph, but before I do any of that, I look for opportunities to factorize. The denominator stays as is. However, in the numerator, I know that there is a possibility that I can factorize this. And with enough trial and error, or use whatever method you want, I know that I can factor this as, let's see, I want to put a 4 here, and I'm going to put a 2 here. So this can actually be factorized to become that. How I factored this, again, that's a different lesson. That's prior knowledge. Let's just go on here. So I factorized this to that, and notice that, watch what happens. Boom. You see what I just did? I just removed this factor. This is a case of a removable discontinuity. And what piece did I just remove from this picture? I removed x minus 2. And what you can do is whatever object you remove, just put parentheses, whatever object you remove, set it equal to 0 and solve. You see that number? That is an excluded value. X cannot be 2, because if you plug 2 in there, you'd be dividing by 0. But the good thing is that we canceled it out, right? We knocked it out. So what does y equal? Y basically equals this, right? Because these pieces are gone. These are gone. That's what I'm left with. Now, what does the graph of this look like? Well, let's check it out. Recall from previous years of math how to graph something like this. Recall that this is just a linear function. The y-intercept is -4, so go down to 4. 1, 2, 3, 4. And then the slope is rise over run, 3 over 1. So rise 3, run 1, rise 3, run 1, rise 3, run 1. So it looks something like this. However, we have to respect the removable aspect of this. We removed x minus 2, which has a solution to. So what you have to do is go to 2, go to the line and put a hole. You literally have to draw a hole. What is the y coordinate? Well, here's what you can do. You know the x coordinate is 2. So take 2 and plug it into not the original, but into the simplified version of the equation. So 3 times 2 is 6 minus 4 is 2. So go to 2, 2, which is right there, and draw a hole. It literally looks like a hole. So this is an example of what a removable discontinuity looks like. And this is how you locate it. You set equal the piece that you knocked out. And whatever that is for x, you plug it into the simplified version to get the y. And you go to that location and you draw a hole in the graph. So that was a removable discontinuity, aka a hole. One more thing I want to discuss quickly is the idea of limit and limit notation. So here I drew just some graph. Here are some problems that I want to work out with you. So all these problems are limit problems. When it says f of x, it just refers to this picture. When it says this tells me where to go. So it's kind of like this. This is an x value, and the goal is the y value. This is your x, you tell me the y. This is the x, you tell me the y. This is an x, you tell me the y. So what exactly is the x coordinate? It's -1 from the right-hand side. Where's -1 at on the x-axis? -1 is right there. And what I can do is I can draw, this is my vertical asymptote. Now, this orange line, I have to approach it, but from which side? -1 is the orange line, but I have to approach it from the right. So here's the right, and I'm gonna come toward it. You see that? I'm gonna come toward it, but I have to be on the blue roller coaster. So here's me jumping on the ride, approaching my hand. And as I do so, what is happening to the y coordinates of all of these points? As I go this way, -1 from the right here, my y coordinates are getting bigger and bigger and bigger. They are approaching positive infinity. That's why this is positive infinity. How about here? Let's approach -1, which is here, but I'm going to approach it from the left-hand side, from this side. So I'm coming at it from here. So I'm coming at it from there. What is happening to these y values? They're going down forever, negative infinity. What about this problem here? What is x approaching? X is approaching negative infinity. Here's my x-axis. I needed to approach negative infinity, meaning I have to move to the left forever. I want to move left. I want to move left. And this piece of the blue allows me to move left forever. You see that? I can move left. And as I do so, as I am on this ride, as I move to the left forever, notice that my y values are sort of leveling off. You see that? They're sort of getting flat. And what is the y coordinate? Here, and here, and here. What are these y coordinates getting close to? It seems as though those y coordinates are getting close to -2. How about this one? Now we're approaching positive infinity for the x-axis. The x-axis is here. Positive infinity means move to the right forever. This portion of the blue gives me the opportunity to move to the right forever. And as I do so, I'm here, I want to move to the right. There I am, I'm walking to the right. And as I do so, what is happening to these y coordinates? They are all, again, approaching -2, right? All these y coordinates, it seems like they're -2. So that's just one example of using limit notation to find limit values for x approaching different quantities.